Hello, my name is Evan Chan, and this is my Physics 2212 Lab 2. For my introduction, the purpose of this lab was to create a computational model of two charged pieces of tape exerting electric force on one another, and then use this model to estimate the necessary amount of charge for one tape to float above the other. And the physics principles that I used during this experiment were Newton's second law, Coulomb's law, electric field of a point charge, and the gravitational force. And the equations I used included F equals K times Q1 times Q2 over R squared, E equals KQ over R squared times R hat, F is equal to MA, where MA is gravity, and F electric is equal to KQ squared over D squared. The main results of this lab were that from lab 1 I got a Q value of 4.43 times 10 to the negative 8th coulombs, and for this current lab I got an updated Q value of 1.40071 times 10 to the negative 8th coulombs, and this difference was about 168.38%. The assumptions I made during this lab were that each piece of tape has the same amount of charge evenly distributed throughout the tape. Air resistance is negligible. Each U-tape can be separated into segments of equal charge, and the total charge on each U-tape is the sum of the charges of the segments. The initial conditions were that the system would be the one U-tape on top, and the surroundings would be the other U-tape and everything else around it. For my code, I have my physical constants, which is 1 over 4 pi epsilon naught, which is 9 times e to the 9th, 9.81, 0.03 for my distance, mass of 0.002, and my charge from the previous lab, 4.43 times 10 to the negative 8 power. And then I calculated the E field for this function, where r is equal to the observation location minus charged particle top position, and then I took the magnitude of r, the normal mar, and I plug the numbers into the electric field equation. For my line charge, for the actual arrows, I have the vector set from distance over 2, top and bottom, so that it would represent the distance. And then I had 15 arrows. For the actual calculation of it, I have this term right here, which is dq top charge times E field dq bottom, dq top position. And then for the net electric force and the gravitational force, I just have the scaling to be Fe on top, and then the scaling for the gravitational force arrow to be Fg scale times negative mg. And then there's my actual code in the results. I got, as you can see, the magnitude of the electric force and the gravitational force are equal to each other. And the orange arrow should be the electric force, and the gravitational arrow is the yellow arrow, and the green arrows are the actual electric force. And for the similarities, our sum of similarities are that the force of gravity and electric force are equal in magnitude but opposite in direction for both labs 1 and lab 2. The calculations for electric force are the same. The differences are that in the lab 1 model, the tape was used as a point charge, while the lab 2 model modeled the tape as a rod split into the point charges. For the what if, I got a point charge model. For the point charge model, I got 4.43 times 10 to the negative 8th coulombs. For the line charge model, I got a Q value of 1.40071 times 10 to the negative 8th coulombs, and the difference was approximately 168.38%. And then for the Y, these estimates differ because they use different levels of precision, as the line charge model is a more accurate depiction of a real world when compared to the point charge model. So the line charge model's prediction for Q is likely going to be closer to the real value of Q. And that's it.